This miniature lecture has to do with enthalpy. So enthalpy is abbreviated H, and the definition has to do with heat flow or the heat of the reaction. So you have to remember energy comes in two forms, heat and work. Heat generally dissipates. We cannot harness that energy that it comes in the form of heat. But we can determine if a reaction gives off heat or a reaction requires heat. And that designation is given by this term enthalpy, which is symbolized by H. But we don't concern ourselves with H. We really concern ourselves with delta H. So this delta means a change in. And typically delta is final minus initial, so the final state minus the initial state. So you could have a delta T, change in temperature, delta T, change in time, delta X, change in difference. In chemistry, we'll be talking about the delta H, and you'll see that a lot, the delta H of a reaction or the enthalpy of a reaction. So final minus initial for a chemical reaction would be products minus reactants. So if we want to figure out the heat of this reaction, generic reaction of A going to B, the change in enthalpy, remember we're going to focus on delta H, not just H, but delta H exclusively. The enthalpy of this reaction, or the change in enthalpy of this reaction to be more accurate, is the change in enthalpy of the products minus the change in enthalpy of the reactants, sort of a final minus the initial, final being the products, initial minus the being the reactants. So final minus initial is your delta. We're interested in the change in the heat of the reaction. In other words, the change in enthalpy of a reaction. So why is this important? Enthalpy gives us a clue on whether or not a reaction will give off heat, this form of energy which cannot be harvested, or will the reaction require heat? Again, heat being an energy that we really cannot harness. So here we want to look at the sign, whether the delta H value, the change in enthalpy of a reaction, is negative or positive. Just look at the sign. If the delta H is negative, that means you have an exothermic reaction, and that implies heat is evolved. So the system really is just your reactants and your products. The surroundings is everything else. So really we could say the surroundings include this beaker, or the surroundings include the room or the universe, to take it to a very, very high level. Anyways, if a reaction is going to evolve heat, then the beaker will turn warm, for example, and the system is giving off heat or evolving heat to the surroundings. We call that an exothermic reaction. Two important things to denote. One, in an exothermic reaction, the delta H is negative. That's important point one. And important point number two is, in an exothermic reaction, energy is a product. So energy is evolved. Contrast that with an endothermic reaction. Now compare this reaction up above with the second reaction down below. And immediately you should realize that the only thing that has happened is that this reaction has been flipped. So now, looking at the second reaction, the products have become the reactants, and the reactants have become the products. So I basically just flipped the reaction. And if you flip a reaction, you flip the sign of the delta H. So a reaction that was once formerly exothermic is now endothermic. In an endothermic reaction, the surroundings give heat to the system. So usually this manifests itself as the beaker becoming cold, as opposed to an exothermic reaction where the beaker or the test tube becomes warm. So here we say the system for an exothermic reaction is evolving heat, giving it to the surroundings. In an endothermic reaction, the surroundings is giving heat to the system. Again, important points. Notice the value of your enthalpy. It's positive for an endothermic reaction. And the second important point, energy is a reactant. Energy is a reactant in an endothermic process. So an exothermic process gives off heat, and endothermic process is the opposite, will actually require heat. And there you see here, an endothermic process requires heat taken in from the surroundings, given to the system. We'll call this an exothermic reaction. Recognize that the delta H will be negative. Also recognize that the products are lower in energy. Now, the flip side is an endothermic reaction. The products are higher in energy. Notice the reactants going to products. The products are of higher energy. Well, where does the higher energy come from? It must come from something that's outside the system. We say the surroundings. That's an endothermic reaction. Let's go over some rules regarding enthalpy or the change in enthalpy. Remember, we're going to talk about delta H as opposed to H now. The first rule is if you have a reaction and you multiply it by a number, for example, 2, 3, or even a fraction, the corresponding enthalpy gets multiplied by that number. So multiply a reaction by 2, the enthalpy gets multiplied by 2. Multiply a reaction by 3, the enthalpy gets multiplied by 3. Here, compare the first reaction with the third reaction, divide the reaction by 2, and we divide the enthalpy by 2. So the first rule with regards to enthalpy, multiply a reaction by a number. The delta H gets multiplied by that corresponding number. It can even be a fraction. So here I have it multiplied by 2/3, and the delta H gets multiplied by 2/3. Rule number 2, the matter of states, solid, liquid, or gas. They really influence the reaction. So solid going to a liquid, this is known as melting. That has a change in enthalpy of a reaction of about 6 kilojoules per mole. A liquid going to a gas is 44 kilojoules per mole. So the top reaction is known as melting. The bottom reaction is known as vaporization. All of these are water, but solid to liquid has a different enthalpy value as opposed to liquid going to gas. So your delta H really matters if you're talking about solids, liquids, or gases. It's all water, but the states matter. So be aware that your delta H is dependent upon whether you're dealing with a solid, a liquid, or a gas, or even, as we talked about in Chapter 4, an aqueous solution. Rule number 3 is stoichiometry. So we always want to balance our equations. And from that balanced chemical equation, we can get relationships. So the relationships from a balanced chemical equation, now that we have enthalpy, has to do with the number of moles coming from the balanced chemical equation. What I mean by that is for every 2 moles of aluminum solid, there is 852 kilojoules evolved. For every 2 moles of iron that is produced, because it's a product, you have minus 852 kilojoules of energy heat produced. For every 1 mole of Fe2O3, iron 3 oxide, that reacts, there's minus 852 kilojoules of energy that is released. So notice that I'm using the term released here, minus. The negative sign tells you that this is an exothermic reaction. Energy is going to be evolved. Energy is going to be on the product side. So these are all different relationships. I have 1, 2, 3, 4, 5 different relationships. You can come up with more relationships. The fourth and final rule with regards to enthalpy is what we've already talked about before. If you flip a reaction, you flip the corresponding sign. So coming back to the very first reaction, this is the combustion of C3H8 propane. You saw this a couple of slides before. This is an exothermic reaction, hence the negative sign on the delta H. Flip the reaction. What was now exothermic becomes endothermic. The delta H sign becomes positive. So an exothermic reaction becomes endothermic, and endothermic reaction becomes exothermic. If you flip a reaction, you also flip the sign of the corresponding delta H. Now let's talk about a different manifestation of delta H. This is delta H at the standard state, also known as standard enthalpy of formation. So how do you measure enthalpy? You can't. You only measure enthalpy relative to something else, relative to some origin. That's where we get the standard enthalpy of formation. This O means not, so standard enthalpy of formation is measured at standard state conditions. So that's something that we want to highlight. Standard state conditions basically mean 1 atmosphere, 25 degrees C, or 1 molar aqueous solution. So that's the specific conditions: 1 atmosphere, 25 degrees C, and 1 molar of aqueous solution. The F means formation. We're forming 1 mole. So this is our basis set. This is the origin upon which all the other delta H's are going to be computed. So The arbitrary scale is the standard enthalpy of formation. Look for that not sign, okay? So if you'll see that not sign, that little O superscript, that means this reaction was energetically determined at standard state, 1 atmosphere pressure, 25 degrees C. To our current slide, and just mention again the standard enthalpy of formation, look for that not symbol for standard state, a very specific set of conditions. Another thing I want to mention is that we look these values up because these are the basis sets, these are the origins. We look these at some lookup table in the back of a book. The basis set comes from the most stable form of the element, the most natural abundant form of the element. As an example, oxygen. Okay, oxygen is not O, but its most naturally abundant form is O2. So that is the reference set of 0. So all oxygen compounds, such as water or ozone, is relative to the naturally abundant state of oxygen found in the most stable state. The most naturally abundant state of carbon is graphite, and that's designated 0. All elements or compounds that have carbon, such as CO2, such as carbon, such as glucose, it's measured relative to graphite. You don't need to memorize any of this, but the point is, look for the word standard, okay, which tells you specific pressure, specific temperature. But you can just look at the table because we really don't memorize these. You can see the most naturally abundant state is the reference point. So for copper, that's going to be solid, not liquid, not gas, and that's designated 0. For oxygen, that's going to be O2, and gas. Remember, states matter when you're talking about enthalpy. And everything is relative to the most naturally abundant form. Now, for oxygen, it's O2, and that's a gas. That's the basis or the origin set at 0. For silver, Ag, the basis or the origin is a solid, not a liquid, not a gas. And that's relative, that's set at 0. So everything is relative to silver solid. That is the enthalpy of those compounds that will have silver in them. So whether it's a solid, whether it's a liquid, or whether it's a gas, whether it's a diatomic, it really depends if that element in its most stable form, in its most naturally abundant form. So the most naturally abundant form of silver is silver solid, and that's designated 0. The most naturally abundant form of nitrogen is N2, and it's a gas, and that's designated 0. So where does this come to utility? It comes in when we're talking about the standard enthalpy of formation, the delta H of a reaction. So notice that not symbol. So you have to be keenly aware that it's delta H not of a reaction, and the delta H of that reaction under standard state condition is the sum of the products minus the sum of the reactants. This N and M have to do with the coefficients of a balanced chemical equation. So you always have to balance your chemical equation. The change in enthalpy is a state function, so we're only concerned with final minus initial. We're not concerned with the mechanism or how we got to that value. We're just concerned whether it's positive, endothermic, negative, exothermic, and this products minus reactants, the sum at standard state tells us that value. Now, this values of delta H formation under standard state conditions, you look them up in the back of the book or you look them up in a table. So let's apply this equation to an example. So here's that reaction one more time. Okay, the combustion of propane, C3H8 gas plus oxygen goes to CO2 and water. So where does this come from, this minus 2,043 kilojoules? Well, under standard state conditions, I can do products minus reactants. So 4 times H2O, the gas form, has a enthalpy of formation of minus 241.8. So I looked at H2O gas minus 241.8. Don't put H2O liquid. You want to put H2O gas. 3 times CO2, so sum of the products minus sum of the reactants. So the CO2 is gas. So let's look up that value for CO2. CO2 gas is minus 393.5. So that's where I got that value. Minus products minus the reactants. So minus, let's put a big bracket here, 5 times oxygen. Oxygen is 0, so when you look it up in the back of your table, 1 times minus 104.7. This is the enthalpy of formation that I found for propane C3H8. So now it's just a matter of math. 4 times 2, negative 241.8 is this value, plus 3 times negative 393.5 is this value. Minus into a minus is plus. And there's your value here, minus 2043 kilojoules per mole. Most students mess up on the math, the distribution of that minus sign. It's products minus reactants, so you have to distribute that minus sign. So under standard state conditions, 2,043 kilojoules are released to the surroundings per 1 mole of propane, per 5 moles of O2 that react, per 3 moles of CO2 that are produced, and per 4 moles of H2O that are produced. There's the equation. I'll give you this equation on the exam, but it's good to remember it for quick access. Some of the products minus some of the reactants. Don't forget to multiply by the stoichiometric coefficient. 4 for water, multiply that value by 3 for CO2, multiply that value of oxygen by 5, and this gets multiplied by 1. So here's another example or an application of Hess's Law. You'll see this in the lab. You'll also see this as a potential exam question. Remember our 4 rules that involve gymnastics or manipulation of this delta H value. So a typical problem that is seen is find the delta H of a reaction. So remember, this means standard state now, the delta H naught. And they want it in kilojoules for this reaction. But this is your net reaction. The other data they give you are these other 2 reactions for this problem, or a problem like this. So the question is, how will you get the delta H for this reaction that is of our interest, given the delta H's of these 2 individual reactions? So remember our manipulations. This, if we were to call this our net reaction, what we want to strive for, and these are our reactions that we somehow have to manipulate to get our net, our final reaction, what we can do is we can flip or multiply using some of our rules. So the first thing I see here is N2O4, that what we want is in the product side, and the N2O4 for this reaction with this enthalpy under standard state is in the reactant side. So if I highlight this as blue, what I can do is I can actually flip this reaction, thus forth flipping the sign. So let me do that really quickly. So what's shown in purple is this reaction that I flipped. So now N2O4 is in my product side, N2O4 is in the product side in the reaction that I want to calculate the enthalpy of. And don't forget, flip the reaction, flip the sign. So 57.2 kilojoule now becomes minus 57.2 kilojoules. Now let's take a look at our second reaction. Notice here that my NO, nitrogen monoxide, has 1 mole, but in my net reaction, the reaction that I'm striving to calculate the energy for, there's 2 moles. And so I think what I could do here is multiply the bottom reaction by 2. And remember one of the rules, if I multiply a reaction by 2, the enthalpy also gets multiplied by 2. Also notice a nice thing that happens if I multiply this by 2, becomes 2NO, plus 2 over 2O2 becomes 1O2, and there's that 1O2 in my reactant side that I also want. So this is very favorable if I multiply the bottom reaction by 2. So let me multiply the bottom reaction by 2. All right, I've multiplied the bottom reaction by 2. I multiplied minus 57 kilojoules by 2. So that turns out to be minus 114. This is exothermic by the negative sign. This is also exothermic via its negative sign. So let's add these 2 together to see if I achieve the reaction that I want to get the enthalpy for. So let's add these up. Realize that the 2 NO2s cancel. So I'm going to cancel that. This NO2, 2 moles on the product side, cancels with the 2 moles of the NO2 on the reactant side. And once I add these 2 reactions, I add the enthalpy. So adding the reactions together, you add the enthalpy. So let's go ahead. I will add these up. I get 2NO plus O2 gas goes to N2O4 gas. So that is my equation that I get from adding these 2, and it matches my equation that I want to get, and the corresponding enthalpy will be nothing more than adding these 2 enthalpies. So add a reaction, add the corresponding enthalpies. So adding these 2 up, I get minus 171.2 kilojoules It's still an exothermic reaction, and it's going to be minus 171.2 kilojoules per 2 moles of NO that react, minus 171.2 kilojoules per 1 mole of O2 gas that reacts, and minus 171.2 kilojoules per 1 mole of N2O4 that is produced.